Hey, welcome back. So let's have a look at a solvent we're all pretty familiar with, and that is water, so H2O. And we can go ahead and we can draw the temperature here, maybe in degrees Celsius on the vertical scale here. And we can look at two things. We can look at the boiling point and we can look at the freezing point. So we know that this is somehow going to depend on the concentration of the solute. So I'm going to write the concentration here. And it turns out that it's not molar concentration that's going to affect this, it is molal concentration. And if you remember, molal concentration is the number of moles of solute divided by the number of kilograms of solvent. So it's very similar for molar for low concentrations, but as we get to more concentrated solutions, they start to deviate. So of course, we know that at zero solute concentration, we just have pure water, and pure water boils at 100 degrees Celsius. And we also know that pure water freezes at 0 degrees Celsius. I'm going to break this axis here, that way I don't have to worry about keeping things to scale. What we find is that as soon as we increase the molar concentration of solute, so if we take something like sugar and dissolve it in the water, if we have 1 mole of sugar dissolved in 1 kilogram of water, we've got a 1 molar solution. And what we find is that the boiling point actually goes up, and I can go ahead and draw a straight line here just to kind of show you what's going on. And at this point here, it boils at, let me see, 100.512 degrees C. And also the freezing point we'll see goes down. It actually goes down by a larger amount than the boiling point goes up, so it's a steeper graph. And it actually goes down to a temperature of minus 1.86 degrees Celsius. And again, if we keep increasing the concentration, so if we have, say, 2 moles of sucrose or sugar in a kilogram of water, the freezing point will go down even further. So it'll go down here to minus 3.72 degrees C. And if we take it down to 3 moles per kilogram here, it'll go down even further to minus 5.58 degrees C. So notice how the water freezing point keeps going down as we increase the solute concentration. And again, the boiling point also does the same thing by a smaller amount, it turns out, which is kind of interesting in itself. But we can see that at a 2 molar concentration, it'll be about 101 degrees, so 101.024. And for a 3 molar one, it'll be 101.536 if I've done my math right. So those are degrees Celsius. So we can look at this and we can say, well, the freezing point seems to be going down. So we talk about a freezing point depression. And we normally calculate change as final minus initial, but in this point here, we're actually going to take initial minus final. So this is going to be the freezing point temperature that you start with the pure water. So that little degree symbol there is going to tell us that is pure water. And we subtract away from that the freezing point of the solution. So the reason for that is that if we take, say, this one right here, right, and we calculate the freezing point depression, it is going to be 0 degrees C minus 1.86 degrees C, and that's a positive number there, so it's 1.86 degrees C. And we have to remember it's a depression, so that means that it is going to go down by that amount. So later on, we're going to write a formula that allows us to calculate how much the boiling point goes up and the freezing point goes down. And you've always got to remember that the freezing points are depressed and the boiling points are elevated. We can do the same thing here for the boiling point. So notice the boiling points are going up from 100 degrees C to, in this case here, 101.536. So we can define a boiling point elevation. And in this case here, it's the new boiling point minus the original boiling point. And the new boiling point, 101.536. The old one was 100. So we can see that that was elevated by 1.536 degrees C. And again, whereas the freezing point was depressed, this is an elevation. So we talk about boiling points being elevated. So let's go ahead and write down a formula for this in the next lecture.